Pluto, the enigmatic wanderer and the Neptune collision hypothesis. Pluto is a remote and enigmatic dwarf planet that was once a part of our solar planetary group of systems. However, recent unexpected announcements made by prominent astrophysicists Neil deGrasse Tyson and have brought Pluto back into the limelight with a startling discovery. They proposed that this frigid world is on a potential collision trajectory with Neptune. But how could this occur? And what would be the repercussions of such a colossal event? Are we witnessing a rare phenomenon in astronomy? Or is there something more to this looming cosmic clash? Join us as we examine the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was partially reclassified as a dwarf planet because of its peculiar orbit, remains a subject of intrigue and research in the astronomical community. According to recent forecasts by leading scientists, Pluto's trajectory is dangerously close to Neptune's, with both Neil deGrasse Tyson and sounding the alarm about a possible perilous collision between these two planets, something that might present a significant threat to Earth. How is such an event even plausible? In contrast to any other planet in our solar system, Pluto's orbit around the Sun takes an astonishing 248 years to complete a single revolution. This means that, since its discovery in 1930, it hasn't even completed one full orbit. But the fascination doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating notably from the nearly circular orbits of the major planets. What gives Pluto its even more unusual orbit is its steep angle of inclination, 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination, combined with its elliptical nature, adds layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. In each orbit, for approximately 20 years, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This leads to a natural question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. Soon after Pluto's discovery, research into its orbit began. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto stood out with its steep inclination and elliptical shape. The mystery grew with the realization that Pluto's orbit actually intersects Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacy of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and impact one another with their gravity. It's like trying to predict, based on where they are now, where they'll go and how they'll pull on each other. In Pluto's case, this problem shows how the paths of Neptune and the Sun's gravity all interact in an intricate manner. The terms vibration and latitude vibration, along with the VSSK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits are vibrations of the astronomical unit, AU. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is important in stopping their paths from aligning. Latitude vibration, on the other hand, refers to the vertical movement of an object in space within its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's located significantly higher than their orbital plane. This adds another layer of protection from potential collisions. Another crucial component in this equation is the VSK oscillation, Vonzipple, named after three scientists, Chi L. and V. who studied how things move in space. It's about how three space bodies like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In the case of Pluto, the VSSK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's motion seems erratic, this oscillation helps keep it moving smoothly for a long time. As demonstrated by the VSSK oscillation, even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or get thrown off course. This three-body problem helps in understanding how these parts change because of the gravitational pull among these space objects. Benefits from studying this. Pluto and our solar system's distant worlds, and their stars, offer valuable insights. Numerical simulations that began in the 1980s revealed that Pluto's orbit, while technically chaotic, maintains stable properties. Minor deviations in initial conditions can lead to significant differences over millions of years. However, these distinctive orbital characteristics were found to preserve long-term stability, effectively keeping chaos at bay. Recent computer tests have helped us understand how the large planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a special connection with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable, with Saturn assisting a bit as well. These tests show that Jupiter's gravity alone is strong enough to guarantee Pluto follows a stable course for an extremely long time, even billions of years. It's as if Neptune, Jupiter, and Saturn are all working together to ensure Pluto keeps moving safely in space, without encountering trouble. These phenomena are essential in maintaining the order and predictability of celestial bodies. Without these mechanisms, the current solar system would be far more chaotic and unpredictable. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions about it possibly crashing into Neptune in the foreseeable future, its orbit is crucial. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbit can reach a condition of equilibrium through the complex interaction between the forces of gravity. Orbital mechanics. Additionally, the significance of constant observation and study of these phenomena helps us better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is an eloquent illustration of this unpredictability. The concept of orbital chaos, which refers to a system's delicate dependence on the initial path taken by a celestial body, is well demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using computer simulations has been very helpful for scientists to figure out how Pluto moves through space. In these simulations, complex mathematics replicate how Pluto, Neptune, and other space objects pull on each other. By altering minor aspects in the simulations, astronomers can see how even small adjustments can make a big difference in Pluto's location during its return. These simulations, which began in the late 1980s, revealed something fascinating about Pluto's path. Even though it has factors like U-vibration and latitude vibration to help stabilize it, its orbit can still be quite wild and unpredictable. If you start off with just a small difference in Pluto's location or speed, over many years its path may ultimately look very different. However, despite all of this chaos, Pluto's orbit remains stable for a very long time, on the order of billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it may seem chaotic at first glance. Predicting cosmic occurrences, particularly when they involve erratic orbits like those of Pluto, poses significant challenges. The inherent unpredictability of these systems indicates that long-term forecasts are frequently rife with uncertainties. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight our predictive limitations. These models rely heavily on the accuracy of initial conditions and the intricate nature of the interactions they imitate. Any insignificant error or oversimplification can result in significantly different outcomes, making precise predictions a daunting task. Moreover, the nature of celestial orbital chaos, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us how much our knowledge of the cosmos still remains limited. Understanding the effects of the giant planet's gravity on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complicated forces endeavoring to prevent such an occurrence? Neil deGrasse Tyson, an important and well-known astrophysicist and a key figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the ways celestial mechanics intersect with the public's fascination with the unknown realms of space. Tyson's position on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views it not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of ongoing education and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much remains to be discovered in space. The fascination with these unknowns, especially the potential interactions between Neptune and Pluto, highlights the dynamic and unpredictable nature of our solar system. Tyson emphasizes that the more we learn about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space. He focuses on the often unpredictable forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about the mechanics of the universe and their broader repercussions for humanity. Kaku's views on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between planets and stars as crucial, not just for academic curiosity, but for their practical implications. The potential collision between Pluto and, for instance, Neptune, is not just a theoretical scenario, but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist outlook encourages us to consider the broader consequences of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. From his point of view, he emphasizes the significance of being prepared for the unexpected in space. His work suggests that the better our understanding of the forces at play, the more equipped we will be to navigate and possibly lessen the negative effects of cosmic phenomena. Tyson and Kaku's views converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on ongoing investigation and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding the current state of the universe's mechanics, but also anticipating how they might change in the future. The potential collision scenario involving Neptune and Pluto serves as a case study for the broader opportunities and challenges in space exploration. It underscores the need for robust research, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, as exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to continue pushing the boundaries of our knowledge. There is general agreement among scientists that, in the not-too-distant future, Neptune and Pluto's orbits will remain stable due to their mean motion resonance and various gravitational influences acting on them. As a result, a direct collision between Pluto and Earth, or even Pluto and Neptune, is extremely unlikely. However, the complexities and possible disturbances in orbital dynamics mean astronomers must continue observing and learning more about these celestial bodies to understand their long-term behavior and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and currently considered improbable, it underscores the importance of continuous research and observation in astronomy. Advances in technology, such as more sophisticated telescopes and computer simulations, will help astronomers improve models and predictions, keeping us informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictable nature of celestial mechanics both reinforce the need for ongoing investigation and adaptability in our understanding of the universe. The potential collision scenario brings attention to the complex and dynamic interactions within our solar system and ultimately reminds us of the vast, still unexplored horizons in our comprehension of space. Through constant research and observation, we strive to uncover these mysteries to ensure our understanding keeps pace with the evolving universe. Pluto's orbit opens up broader discussions about the solar system's stability. While Neptune and Pluto's relationship is intriguing, it reflects the governing gravitational interactions that affect all celestial bodies in our cosmic neighborhood. Every planet, moon, and dwarf planet experiences a delicate balance, where their positions and motions interact in ways that occasionally appear counterintuitive. This complexity challenges our understanding of what is stable and what is not in space. Astronomers constantly face the challenge of predicting long-term orbital behavior, as small changes can ripple through space over billions of years. While Pluto's path may appear unpredictable at first glance, the cosmic forces at work ensure that these bodies remain in a harmonious state for incredibly long durations. However, even small changes in a planet's orbit, or an unexpected gravitational force from another celestial body, could disrupt this balance. Such an event could alter the course of planets, moons, and even dwarf planets like Pluto, creating ripple effects throughout the solar system. Because of this, it remains crucial for scientists to continue refining their models and studying the movements of these distant worlds, ensuring they are prepared for any unforeseen cosmic shifts that may occur, no matter how unlikely. Through this continuous observation, we inch closer to a deeper understanding of the universe.